Welcome, everybody, to our first monthly engineering AMA here over at Hemi. We are trying a different format, so hopefully, wherever you are viewing, you are viewing. I almost said welcome to midweek with Max, but it is not that, even though we're wearing the sweatshirt. But welcome to our ZK Provability AMA. And without further ado, let me kick it over to Max because, as we all know, he has a lot to say about ZK Proof.
All right, welcome everyone. Hopefully this new streaming platform is working correctly. And I think we also, somebody gave Rick access to sound effects. So why don't we test those out real quick. And we'll start off with a really terrible joke. So no matter what happens today, everything's going to go uphill from here. What is a parrot's favorite part of the Planck proof system? The polynomial commitment scheme. All right, we got everything working. Cool. All right, with that, I guess a quick intro. So this is all about ZK provability and what we're doing at Hemi that uses ZK as part of our technology stack. So a couple different areas that we're going to be probably diving into today based on community questions. So the biggest is the HBitVM proof system, which is the ZK proving system that uses Bitcoin, Ethereum, and Hemi's features like HVM and proof of proof to create a more secure way to generate completely self-contained proofs that can be used both for Ethereum settlement, but also for Hemi's settlement back to Bitcoin using a modified BitVM style design. So we can talk about the actual proof system or anything about the overall HBitVM design in general and how it differs from BitVM style or BitVM2 style technologies. We're also using ZK proofs to improve threshold signature scheme systems, which we're using for what we've been codenaming our MinerFi system, our upcoming fast bridge system for onboarding Bitcoin more easily into the ecosystem and composing it into DeFi. And then we're also working on some infrastructure around decentralized ZK proving using a ZK compute marketplace. And so that's a way for the Hemi network itself to incentivize ZK proofs for its own use in HBitVM for, again, Bitcoin and Ethereum settlement, but also a way for third parties to use it if they're building apps in the Hemi ecosystem or the entire blockchain ecosystem and want to use a decentralized compute network. And it also serves as infrastructure for a future chain builder, L3 plus, build your own chain in the Hemi ecosystem toolkit. So with that, I will kick it over to Rick and we can start going through questions. Or we could do a round of intros.
I was a little early on that applause. I apologize.
No worries. Do you want to go around the table and do intros real quick and then jump into questions?
Absolutely. Do you want me to give quick ones or should we all just do it?
Why don't we just go around the table? So I'm Max Sanchez, CTO of Hemi Labs, working mainly on consensus protocols and backend design of the HVM system that allows smart contracts to communicate with and read data from Bitcoin. And I'll throw it over to JCV next.
All right, I'm John. I'm VP of Engineering, which means I jump in and do various engineering things in various places, whether it's worrying about security or trying to keep other engineers on track or, reviewing code or helping write the white papers. It's just whatever engineering things there are that are around, and yes, a disordered mix of things.
You didn't kick it to the next.
I didn't kick it to the next.
Popcorn Clayton.
Yeah, Clayton. Europe.
Hey everyone, I'm Clayton. I'm an engineer here on the Hemi Labs team. I mainly work on writing software for the many daemons that make Hemi work and run. Also a little bit of infrastructure as well, help set up the internal nodes that help run our network. But yeah, just continue to work on that and making sure it's stable and adding features as required. Yeah, that's what I do. And I'll pass it on to Joshua.
Hello, I'm Joshua. I'm a software engineer on our protocol engineering team and our security team, and I primarily work on a bit of everything from infrastructure to the security side of things and all of the core components and then some. And people regularly see me in the community because I help Rick with a lot of the Discord parts, and basically I appear everywhere.
Josh does appear everywhere. I'm Rick, head of community here at Hemi, and I'm kind of like a comic relief for protocol engineering, and also the Robin to their proverbial Batman, I like to think at least. Um, hold on, let me all right, there we go. Sound effects are still working, boys. All right, with that, let's
Oh, come on. You didn't have like a Batman like pow or something like that sound effect to go with it?
hold on. That's the closest I got.
Yeah,
We're gonna I promise this is only the first one. So by next time we're gonna have all sorts of new sound effects. Don't you worry about that. But let's hop directly into questions.
Actually, Rick, before questions,
What?
would it help maybe a 30-second max what ZK is? Like,
You think that's gonna be 30 seconds?
No, I was going to say I'm not sure 30 seconds, but we can do a short version.
I'm an optimist, people, but no, but just like the intro for like, just to set the stage, like ZK, zero knowledge, just something there to.
All right, hold on. I have a sound effect for this.
Uh-oh. All right, yeah, so super quick intro. We'll try to keep this short, and we can also dive into just general questions about ZK if people are interested. ZK stands for zero knowledge, so we have all kinds of different zero knowledge proofs. Zero knowledge basically means that you can prove a computation without having to provide the actual input data that you fed into the program or into the relation that you're proving, but you can still reveal the output of that computation. So basically a bunch of people agree, or at least two parties agree, on a computation they care about. One person can have private data. They can run the computation with that private data. They can produce a proof, and they can give it to all those other parties and convince them that they did the computation correctly with some unknown input data and got this output data. And in blockchain engineering specifically, we're usually referring to ZK proofs that are also succinct, meaning that the proof size is very small relative to the computation size. So for example, you could prove execution of an entire 4 megabyte Bitcoin block, but the resulting proof that you validate is only, say, 200 bytes. And they're also non-interactive. So there's two types of ZK proofs. You can have interactive and non-interactive. So interactive is one party convincing another party, and they're going back and forth exchanging messages. So it's sort of challenge response. And then non-interactive, there's usually ways to turn interactive proof systems into non-interactive ones. And a non-interactive one allows the prover to independently, on their own without communicating with anyone, produce a proof of the computation and then provide that proof publicly that can convince anyone that the computation was completed successfully and gave this output. And then usually there's two main types of proof systems that we care about in the blockchain ecosystem, or categories of proof systems. There's ZK snarks and there's ZK starks. Won't get too much into the difference between them right now, but a lot of the way that we're using ZK proofs, we're using both in a Stark to Snark pipeline. So we get the computational speed benefits of ZK Starks, but then we're wrapping things in a Snark proof, which is much smaller, much more computationally efficient to verify when it actually goes on-chain or gets sent over peer-to-peer for verification. So that's super high level. And then a couple examples of why you might want to use a ZK proof. Usually, well, in the blockchain space, it depends, but even though we all refer to them as ZK proofs, a lot of the use cases don't actually care about the ZK part. It's just sort of how people use the term colloquially. But zero knowledge, again, refers to the privacy of the input data to the proof. And a lot of use cases of ZK proofs actually only care about the non-interactive, succinct argument of knowledge part of the proof, which means that you can quickly verify a computation was done correctly and give a certain output result, and that the prover does have some knowledge of the input witness that was able to generate that proof. And often the input data to the program is actually public. So it could be, for example, ZK proving the state transition of an Ethereum block, and everyone has access to that Ethereum block, but somebody with a really powerful computer generates the proof, and then they can give that proof to a light client who then doesn't have to rerun the block execution or download the block in its entirety. They can just validate the proof of the computation. So ZK originally started as primarily focused on just that zero knowledge property of being able to maintain privacy of that data. But now a lot of the use cases and some of the use cases that we're using it for at Hemi really benefit or don't benefit from the zero knowledge property, but they do benefit from the succinctness, the fast verification, and the ability to prove arbitrary computations.
So one other bit on that arbitrary proving thing. Remember, in crypto, you're always in a situation where there's some amount of you need to be able to trust untrusted parties, more or less. With your bank, you have a trusted party that trusted. Whether or not you trust your bank is another thing, but you're sort of stuck trusting it. The point of crypto is, or one of the points is that you've got a whole bunch of untrusted parties in the big bad internet out there, and you have to be able to have some way to prove that you can trust them on certain things. And the zero knowledge, proofs give you an ability to do that. For someone to prove, even though you have no reason to trust me, I can prove that I'm being correct on this particular statement.
And to give kind of an extension there, so one of the main innovations of Bitcoin was proof of work. Not that Satoshi invented proof of work, but found a unique, interesting way to use it for distributed consensus. And so proof of work basically allowed all these mutually distrusting random anonymous parties on the internet to all agree on a certain state of something. And ZK proofs are sort of complementary to that, where now instead of having to reproduce computations in order to all come to agreement, you can instead validate proofs that effectively replace or act as verifiable proxies for that compute to come to that agreement. So you still need the underlying consensus protocol. It's not replacing it. But for blockchain systems that have a decentralized consensus protocol, ZK proofs basically convert your, they wrap around your consensus protocol in order to allow you to establish that trust in a more direct, lightweight manner for, say, light clients, or more importantly, in a lot of cases, verification in a computationally constrained environment like another blockchain. So I think with that, we will hop over to questions.
All right, sounds good. Our first our first question has 4 parts. So we will treat it like 4 questions. So Mudakan asks, first question, part A. If you had to explain to someone why Hemi ZK is different in one sentence, what would you say? Is it more about making the Bitcoin Ethereum combo provable, or more about raw speed scaling, or both?
That's an interesting question. So we're using ZK proofs in a couple different ways. I'm going to assume this question is mostly focused on HBit VM and what we're doing between Bitcoin and Ethereum with ZK proving. So just as a little bit of quick background on that, with HBit VM, so basically Hemi is an L2 that is connected both to Bitcoin and to Ethereum. So it's using Ethereum for DA, it's using Bitcoin for Bitcoin finality with a consensus protocol called proof of proof, and it has a Bitcoin node embedded inside the EVM that smart contracts can talk to. So it's sort of that baseline of understanding of what Hemi itself is architecturally. What we're doing with HBit VM and the HBit VM proof system is we are using the properties of Bitcoin and Ethereum together. So backing up a little bit, zero knowledge proofs always have to validate within a certain context. So for example, especially in the blockchain ecosystem, obviously there's trivial stuff like proving the factorization of a number or something, but in blockchain, there's always a context that a zero knowledge proof is validated against. So you can, for example, validate that Ethereum block 100 is a valid Ethereum block, but that needs the context that somebody validating that already believes block 99 is valid. And specifically in the case of BitVM, which is a technology used to build Bitcoin bridges to other types of networks, you have to validate a ZK proof on Bitcoin in a very constrained environment. And so usually on Bitcoin, or always on Bitcoin, you don't have access to a lot of additional context about the current Bitcoin chain. So if you look at Ethereum, for example, if you build a ZK proving system that settles an L2 to Ethereum, Ethereum can look at itself. It has self-introspection. And so Ethereum is able to say, hey, I'm validating a ZK proof in my block 100, and it proves that this L2 is valid based on some data that came from Ethereum block 90. And they can check that that block 90 is actually an ancestor of the current block in which the execution is occurring. On Bitcoin, you don't have that. On Bitcoin, you have access to very limited information inside of a Bitcoin scripts execution. And so what we're doing with HBit VM is we are using Bitcoin and Ethereum together to create self-contained ZK proofs that need very minimal external context. So normally for BitVM systems, you need a ZK proof that validates against a certain known Bitcoin block. And without getting into the details, we can obviously dive into it, but basically the ZK proof proves that as a Bitcoin block 100, an operator of the system did something correctly. They correctly fronted liquidity in the system. And so in Bitcoin, when you validate that and release funds to that operator who submits a ZK proof to the network, your ZK proof has to operate in the context that that block 100 is really canonical on the Bitcoin chain. And since you don't have that ability like you do on Ethereum to look back at Bitcoin's history and say, okay, I'm executing in a chain that has this block, there's all these weird workarounds. The original one in the BitVM 2 white paper was superblock light client emulation. There's a lot of other approaches that other projects have used to try to get around it, but they usually end up introducing more centralized parties or more protocol complexity. And so with our proof system, we're able to construct these self-contained proofs that can be validated on Bitcoin in a similar way to existing BitVM 2 or BitVM 3S style designs. But the only context they need is a timestamp. So you feed them a timestamp and they can prove anything about Bitcoin, Ethereum, or the Hemi network, or by extension, really any blockchain that uses Ethereum for DA, with only needing a timestamp as the context for basically a recency check, if you will. And so the way we do that is we essentially take Ethereum data and publish it to Bitcoin through a decentralized protocol. And then we take, we already have Bitcoin data being pulled up into the Hemi network through that embedded Bitcoin node inside the EVM. And by combining those two together and then adding some constraints to our ZK proving system that basically checks the validity of Bitcoin against Ethereum and Ethereum against Bitcoin based on their common knowledge that's sort of sucked up through the Hemi's awareness of both chains, we can build a ZK proof system that can prove anything about Bitcoin or anything about Ethereum. And if you wanted to forge it, you would have to attack both of those networks. So you'd have to 51% attack Bitcoin and simultaneously perform a consensus attack on Ethereum to produce an alternate fake chain in order to produce fake proofs of either chain. So you have this sort of, you can think of the two chains running together and being sort of tied together by, lace run between the two chains that validates each one in the context of the other, and then uses Hemi as a way to observe all of that and ZK prove it. So with that context, and that was a little long, but basically in that HBitVM proof system, we're trying to make, the main thing is focusing on security and correctness of proofs about Bitcoin, Ethereum, and Hemi. And so it's not necessarily about speed. There are ways that you can use this in some aspects that could speed up some cross-chain interoperability protocols. But the main focus is really how can we use Bitcoin's proof of work, Ethereum's proof of stake, combine those together to create a system secured by both that can generate ZK proofs that can exist with only the context of a timestamp for their own validity, and then use that to prove anything about those networks we need for cross-chain interoperability protocols. So to answer the question, it's much more about proving both of those networks and the Hemi network as well in a very secure and self-contained manner. It does let us do cool speed and scalability things. So it lets us settle to Ethereum faster because we can settle with ZK proofs that prove correctness of the Hemi chain instead of needing any sort of fault dispute system. It does also lend itself to scaling. It can be extended to Hemi's future chain builder L3 ecosystem, where you have all these different chains that are ZK proven and settle to Hemi, and then you can extend this proof system to create ZK proofs of those L3s to allow them to quickly interoperate with the rest of the blockchain ecosystem and each other. But the main thing is really focusing on making proofs of Bitcoin, Ethereum, and Ethereum DA-based L2s like Hemi more secure and more self-contained, meaning they can be used in more interesting contexts.
All right. We have reached part B of question 1.
We're moving along.
Trucking right along, boys. All right. In the tunnels to Ethereum, you're planning a 2 of 3 redundant ZK proof system. How does that actually make bridging safer than a regular bridge or a single proof ZK rollup, especially when moving BTC native stuff like ordinals or runes?
That's a good question. I think JCB might have some interesting insights on this too from more of a security posturing perspective. So ZK proof systems, I'll try to keep this one short. Fundamentally, they can have bugs. And so when you build a ZK proof system, at least the way that we're doing it using something called a ZK VM, which is this sort of general compute environment where you can prove any program that you can write in a language like Rust and that runs in deterministic time and eventually halts and finishes, and that you can compile to an architecture like RISC-V or MIPS, you can run that program as a guest inside of this ZK VM. And so it used to be that ZK proofs needed, excuse me, you to write these custom circuits, or in the case of Starks, a custom error. And you had to implement your program logic in this really complex, sort of non-intuitive system. It was very brittle, and if you change anything about the protocol, the actual proof system, the actual proof program rather that you're creating had to completely change and be re-audited, rechecked. ZK VMs let you just write in these high-level languages. They're a little bit less efficient because it's kind of the analogy of an ASIC to a CPU. You know, a Bitcoin ASIC is, say, really, really good at Bitcoin mining and calculating SHA-256D hashes, but that's all it can do. And whereas a CPU is not great at calculating SHA-256D, but you can compute anything on it. So sort of similar where we're using in everything that we're doing at Hemi ZK VMs, which let us write things in higher level languages, make modifications to them much more easily, audit them much more easily. And so with that sort of a construction, you have two layers. You have the correctness of the underlying ZK VM system, and then you have the correctness of the program you implement and run in the ZK VM. And so for there's basically two layers where something could theoretically go wrong. So focusing on the ZK VM layer first, if the ZK VM system is implemented in a way that is what we call under-constrained, meaning that the way that you build ZK proofs is basically you have all these constraints that apply to a computation. So you could say in a ZK VM context, for example, when you process the state transition in a RISC-V environment and the next instruction is an add, and you're adding the numbers in these two registers and putting the result in this third register, you'd have constraints in the system that enforce the addition was done correctly, that the right registers were read, and it is the result of addition on those that is now saved to this register. If you're doing a memory access, it'll prove correct access of that in another separate memory structure. And so these constraints basically enforce the correct execution of the emulated CPU environment that the ZK VM runs. And if there is a missing constraint in that system, for example, they don't properly constrain one of the registers for an opcode, or they don't properly constrain some pattern of memory access, then you can get issues where somebody could manipulate that proof system and inject basically malicious data or a malicious branch in the code that's being executed in the ZK VM while they are generating a proof. And they could create what looks like a valid proof, or what technically is a valid proof, but of a manipulated computation that you can't detect. And so that sort of an implementation bug in a ZK VM means that if somebody found a way to abuse a under constraint, for example, to manipulate a jump instruction to jump arbitrarily to another part of the program that they wanted to execute, then they could potentially bypass what you think you're proving and generate proofs of something else entirely that still validate within your system. And so the multi-prover architecture basically is a defense in depth measure against that sort of exploit. So it's very unlikely that, say, RISC-0, SP1, and OpenVM, which are three popular production-ready ZK VM systems, all have the same missing constraint, or all have the same implementation bug somewhere else. And so by using multiple together, you basically protect against one of them having some under-constrained issue somewhere that somebody could use or abuse to create an invalid ZK proof. And then on the second layer, you have the actual application that we at Hemi Labs, for example, would write and run in a ZK VM. And sort of the future V2 of a multi-prover system is we could potentially have multiple implementations as well of that guest program that operate differently but should fundamentally do the same thing. And so you could do multiple proofs of different guest programs in multiple proofs of different ZK VMs. Our initial approach is just going to be one guest program, but run in multiple ZK VMs. But that's sort of a step two extension of that defense in depth measure.
Yeah, and just to add, so the defense in depth part is important because ultimately, in cases like this, you're as secure as you're willing to pay to be. Where in this case, pay really means how much either compute time, developer time, or whatnot you want to spend on it. So if you take like in Max's example, where you have, if we start out where we have multiple, VMs and you pick, you sort of have two or three means as long as two of them agree, it's unlikely that you have the same bug in both. If you were to go even further and have, the different pieces written by multiple places, you're even more secure, but it always depends on how high value the transaction is. For most things, you know what? If you can have two or three VMs agreeing, the cost to attack that would be more than the vast majority of transactions you would ever want to do. And it, even for when you talk about these Bitcoin native things, deep down, they're not that different from any other transaction or any other transfer or any other computation, other than that we tend to assign more value to them. So it just means that the type of thing like the Hemi one, where if we could do the two of three, that's a little better. It means we can put more faith into it. Ultimately, there's nothing fundamentally different about any of those, just how much power, how much computation time, how much engineering time, how much time / money, because the two are pretty similar, are you willing to put into protecting a thing? To us, I would argue that, if you could have a two of three redundant ZK proof, that's still really good. That is a lot more defense and more layers than you have in most things anyway. So is it perfect? No, but security is never perfect. There's no such thing as perfect security, just like, there's no such thing as a unsinkable ship. We all know what happens when you call your thing unsinkable. Rick, I was hoping for some sound effect on that. Come on.
You get a movie made about you.
Yeah. And security is the same. You do as well as you can based on what you're trying to secure.
And I'll also add to that, there's a bit of a nuance on the implementation side and sort of a difference between the Bitcoin and Ethereum side too. So with ZK VMs in general, most of them, if not all of them, use Stark proofs, which are very big, but they're computationally more efficient to generate. And then they get wrapped in a Stark proof, kind of like I mentioned earlier on in the live stream. And so there's defense in depth at multiple layers sort of inside the ZK VM as well. So there's the security of the Stark proving system that you're using to actually prove the computation. And then there's the security of the Groth 16 or, Plonk wrapper or whatever you're using to wrap that into a snark that's more efficient to verify on-chain. And so on Ethereum, it's reasonably inexpensive to validate 3 independent full Stark to snark pipelines. So you can have, risk 0 and generate a ZK proof of your guest program, and then wrap that in a Groth 16 proof. And then you can do it with SP1, wrap it in a Plonk proof, and then you can use OpenVM and do whatever on their side. I don't think they support Groth 16 yet, so Plonk or whatever they're using currently in their system. And you can validate all of those simultaneously, or at least 2 or 3 of those on Ethereum natively. So those are 3 completely independent pipelines. The issue is on Bitcoin, you're much more compute constrained. And so BitVM3S sort of addresses this with garbled circuits and moving a lot of the computation or a lot of the complexity sort of off-chain to this giant garbled circuit that gets opened at various points. But in general, on Bitcoin, it's much harder to validate even a single ZK proof, and getting a Groth 16 verifier small enough that it could actually run inside Bitcoin. And again, it's not run inside like one single Bitcoin transaction. It's a giant 2 gigabyte circuit implemented in Bitcoin script that's chunked out into all these different pieces, and then use an optimistic system to actually choose which piece you bring on chain to prove a malicious computation. But getting it small enough that you could even commit to the state transitions between all those chunks of the programs was itself a giant engineering feat by people engineering in the Bitcoin bridge technology space. And so verifying 3 independent snark proofs on Bitcoin is probably possible, but it's not very practical. Again, with BitVM 3S, it becomes easier to do, or potentially with an approach like BitVMX. But so on the Bitcoin side, you may need to, and one of the design decisions we're currently figuring out for the initial version versus a future version with BitVM 3S where we have more flexibility, but is having to wrap all three of those Stark proofs in one single Groth 16 proof. And so that would mean you get the security against any missing constraints in the three ZKVM implementations of the Stark prover, but you do still have that one central point of failure in a much smaller part of the overall ZK proof pipeline, which is the Groth 16 wrapper for the Stark proof. So you'd have if there were constraint issues in the Stark proving systems of any one of those ZKVMs, you're still completely safe. But if there was a issue somewhere in the Stark to Snark pipeline of whichever one of those you choose to use to wrap all three of those Starks into one single Snark you can validate on Bitcoin, you do still have that one much smaller attack vector that doesn't have that redundancy. So again, future ways of making compute verification on Bitcoin more efficient will probably allow us to do the full end-to-end, 2 of 3, or even at some point you could theoretically do 3 of 5 or whatever computation where you have the complete Stark to Snark pipeline completely independent for all of the ZKVMs you're using. But with a lot of the current designs, you do still have that one sort of final funnel that everything has to feed into, ultimately one Groth 16 proof with a lot of BitVM style designs today.
So another point on that is the sort of bigger, more complicated or newer something is, the more important multiple independent versions of it that can sort of compare against each other are. So like Groth 16 is a pretty well-known, well-understood thing. There's less likely to be bugs hiding in your implementation of that. It's kind of like if you were to just do SHA-256. We all know how to do that. Bugs in that are findable and demonstratable, and it's not likely to be your problem. As you start getting into things that are newer, that don't have years and years of libraries that do it, that have been verified over and over again, it's more important to have redundancy because there's more, the likelihood of a bug, and even better, better or worse, depending on which side you're on, the likelihood of, have about 2 independent implementations having the same kind of bug is radically different.
There's that sound effect you expected last time.
Thank you.
I'm trying to temper myself with the sound effects. I don't want to, blow the whole load in one show. We have many of these to do, so we can slowly roll out the sound effects. All right. Moving on to part C. For regular devs or users, what will change once the HVM is fully ZK provable? Will smart contracts be able to do Bitcoin checks instantly and trustlessly, or is there still a wait period like with today?
Good question. So fundamentally, HVM runs behind Bitcoin's tip by, generally speaking, 2 blocks for a reason, and it's not related to ZK proofs. So the reason is because it's actually a data availability problem. And so we're preventing against a data availability problem causing a liveness problem on Hemi. So as a quick overview for anyone listening and who isn't too familiar with how HVM works, like I mentioned earlier, we have this Bitcoin node that is a custom Bitcoin node that we implemented that has a built-in indexer that indexes a bunch of Bitcoin data. And as with anything in blockchain, if anyone's executing a transaction in, doing some computation in the same transaction in the same block, if they're not doing it on the exact same state as all the other nodes on the network, you're going to get a state divergence. As a dumb example of that, if on Ethereum, 2 different clients were to implement, say, an opcode differently in some edge case or precompile differently where, some sort of SHA-256 hash of data above a certain length was padded differently or something, you'd get a state divergence because their computations diverge, and then what they ultimately end up computing and the execution paths they take through the transaction are going to change, and they're going to end up committing different data to the Ethereum state tree. So similarly with HVM, to prevent that from being an issue with smart contracts being able to query Bitcoin data, that embedded Bitcoin indexer needs to be fully deterministic based on chain state. And so we have this thing called a Bitcoin attributes deposited transaction, which, if you're familiar with Ethereum L2 architectures, is very similar to the existing attributes deposited transaction that brings Ethereum state on chain. Works a little differently, but conceptually very similar, where that acts as a deterministic clock of Bitcoin's current state as known by the Hemi protocol at a certain point in time, that then is used to update the deterministic Bitcoin indexer to the exact same state across all nodes that are executing the exact same Hemi block at whatever point in time, wall time they're actually doing that. And so the reason HVM runs 2 blocks behind is because if somebody were to, say a miner were to maliciously go and generate a Bitcoin block and then relay the header of that Bitcoin block to the Hemi network in one of those Bitcoin attributes deposited transactions, but not relay the full block to the Bitcoin network, it would create an issue where Hemi nodes cannot advance their HVM embedded Bitcoin node indexers onto that Bitcoin block that the Hemi execution environment expects. And so you'd get an issue where you have a bunch of nodes who don't know about a Bitcoin block, but they need that Bitcoin block in order to update their Bitcoin indexer state to correctly process transactions that are going to agree with the rest of the network. And so by lagging 2 Bitcoin blocks behind, we basically make that attack extremely hard to do and prohibitively expensive for Bitcoin miners. So they would have to, A, throw away valid Bitcoin blocks to attempt the attack, and B, by making it multiple Bitcoin blocks instead of just one, they would need to bet on their own ability to outrun the existing Bitcoin chain for a relatively long period of time within that 2 Bitcoin block window. They're competing against the network, creating 3 alternate Bitcoin blocks. And so it makes it very, very difficult, if not impossible, for even a fairly large Bitcoin mining pool to do such an attack. And so that doesn't change with ZK provability, because you could theoretically design a system where the sequencer ZK proves all of the HVM precompile calls in real time. So the question makes perfect sense in that there is a reframing of some roles on the network that could make HVM state available a little quicker using ZK proofs, which could at some point happen in the future, but it would require that everybody on the network be only validating ZK proofs of the Bitcoin state instead of full nodes validating it against a full Bitcoin indexer, which is a architectural design trade-off in some regards. So there is potentially ways ZK proofs could do that, but not the way that we're initially going to use it.
But also there's the important fact that there's no such thing as the current Bitcoin block. There's the current Bitcoin block that you know about.
It's like relativity.
Yes. So since as each block, as your blocks get older, the likelihood that, your blocks are the ones that are set in stone and are the quote unquote real history of things gets higher. So if you were to always say, what is the current block? You're making a probabilistic statement. And if you want determinism, which is what we want in HVM, determinism and probability don't really play nicely together. So having that little delay makes things deterministic in a way that both simplifies and also makes things more safer, accurate, however you want to look at it.
All right. We are in the final stretch of question 1. Moving on to part D. Yes, this is still question 1.
You should have just lied and said these were all different questions.
I really should have, but it's a great question. I mean, and let's be honest. Are you going to run out of things to say about ZK provability?
No, I think we're already looking at running long today. We're still on question 1 technically, so we're
we're doing just fine here. All right. So part D, question 1, still from Mudakon. Let me say that again in English. How does the ZK work you're doing on the Bitcoin side, BitVM2 plus HVM, let Hemi do things that pure Bitcoin L2s or pure Ethereum ZK chains can't, like actual DeFi or yield on native BTC without wrapping or custodians?
Another really good question. So fundamentally, I won't rehash what I already sort of covered about the HBitVM proof system, but essentially using Bitcoin and Ethereum together lets us create more secure ZK proofs of Bitcoin state and Ethereum state and Hemi state that we can also use in a very context-constrained environment like Bitcoin, where you don't have access to, again, a lot of the usual context you would designing a normal ZK-proven application in, say, the Ethereum ecosystem. So from a practical perspective, most other protocols can't generate this kind of proof for themselves, or if they were to do it, it would be a lot harder, and there's more moving pieces that aren't really synchronized together in some deterministic way. So because Hemi sits between Bitcoin and Ethereum and has knowledge of both chains, can pull certain relevant information out of Bitcoin with its embedded Bitcoin indexer, can get certain knowledge of Ethereum from its view of Ethereum that's sent in through Ethereum attributes deposited transactions by the protocol. And also on the Ethereum side, ZK proving and validating ZK proofs of stuff's just easier because Ethereum is more flexible anyway. But being connected to both of those means that Hemi can sort of synthesize the current state of both of those chains in a way that is they sort of advance together, and you can look at them in the context of each other. So you can look at Bitcoin and say, hey, is this Bitcoin chain, what's the total proof of work of it? Is it being advanced by, at the expected rate of Bitcoin mining with some sort of, allowance for bad mining luck or, natural drops in the Bitcoin hash rate? Is this Ethereum chain advancing? Do we have, this is the new part of the HBitVM proof system, do we have publications of Ethereum attestation data to Bitcoin such that if somebody were to be trying to manipulate this proof to create an alternate version of Ethereum, and thus an alternate version of the Hemi chain based on alternate DA data of the Hemi chain published to that fake Ethereum chain, that they would be revealing enough information that somebody would be able to extract that out of the system and slash the Ethereum validators who are making that fake chain? Is the Ethereum chain finalized with a certain percentage of the total Ethereum consensus power? Is the Bitcoin chain being advanced in lockstep with Ethereum within some certain time bound? So the Bitcoin chain that we know about is not, 24 hours behind the Ethereum chain we know about, and that Bitcoin knowledge is ultimately contained or wrapped within Ethereum through Hemi's DA publications of Hemi state, which includes knowledge of Bitcoin state to Ethereum. Is that roughly in line with the current Ethereum chain progression? And so by using all those different properties and combining them into a ZK proving system, you basically use Bitcoin's proof of work and Ethereum's proof of stake together in a way that compromising the system requires you to attack both of those systems simultaneously. Or you would have to, if you were in Ethereum, you control a lot of Ethereum consensus power, you would be exposing yourself to huge slashing in order to forge one of these proofs on the order of, billions or tens of billions of dollars to manipulate the system. You can either do that, or you can also 51% attack Bitcoin to bypass that slashing, but then you have to 51% attack Bitcoin, which is a very, very high bar for, cryptographic or cryptoeconomic security of the system. So back to the point of the question, what can you do with those proofs that you can't do on other pure Bitcoin L2s or pure Ethereum L2s? So the first thing is you can't generate those proofs with any sort of other architecture that's only looking at one system. You have to have an architecture that is looking at both systems. One of the cool things is, because we're in between both Bitcoin and Ethereum, these proofs that we generate could be reused in the ecosystem more broadly now that there is a project, Hemi, that's generating them. But to actually generate the proofs themselves, you need a blockchain with an architecture like Hemi has with this dual L2 architecture. As far as what you can actually do with it, the fact that these ZK proofs can be validated and securely used with the only context being the actual timestamp of the environment in which they're being validated means that you can build much more flexible designs of stuff that's validated on Bitcoin. And you can also validate information not just about the Bitcoin L2, but about pretty much anything in the Ethereum ecosystem you want to use as part of your proof. And so from a practical perspective, our initial use case of that is, of course, the HBitVM tunnel. So being able to securely store Bitcoin in a ZK protected vault that can only be withdrawn from if somebody proves that they correctly burnt the respective amount of Hemi BTC on the Hemi L2 layer and deserve to be allowed to withdraw the underlying Bitcoin. In practice, it's a little more complicated. You have an operator who fronts liquidity, and then the operator uses ZK proof to get reimbursed by the system, but same end result. But you can also remix that core technology, that HBitVM proof system, and the basic ZK verifier. You can extend it with additional application-specific proofs. So HBitVM tunnel, that's one application proof that's built on top of the sort of foundation of the HBitVM proof system. You could also build an application-specific proof for something like a Bitcoin-backed stablecoin protocol. So you could say, we have a DeFi protocol that's running on the Hemi network inside of HVM, and it's going to mint this synthetic stablecoin against over-collateralized positions on Bitcoin that are secured by ZK proofs. And then you're no longer talking about minting, Hemi BTC and then redeeming it to get to the underlying vault. You're talking about the underlying vault, the Bitcoin in it only being redeemable if somebody burns the correct amount of stable coins to bring the system back into correct collateralization. And then they can withdraw a portion of the Bitcoin out of the system for, say, stablecoin redemptions. And you could use a Bitcoin to USD price oracle from Ethereum, because we also have access to Ethereum data. Or you could build a native Bitcoin settled lending protocol. So you put up Bitcoin in one of these vaults that's secured ultimately by validation of one of these HBitVM extended proof system proofs. And you could say, okay, Alice put up 1 Bitcoin and Bob then lent her, 50,000 USDC on Hemi or Ethereum or wherever. And looking at this oracle that exists on whatever chain we want, we can see if that loan is, sufficiently collateralized. So if the price of Bitcoin or Ethereum or price of Bitcoin or USD fluctuates, we can detect whether the loan is underwater, getting close to underwater, needs to be liquidated. And then you can have conditional logic for who is allowed to redeem all or part of that Bitcoin that's held in ZK secured vaults on the Bitcoin side based on that oracle data, and then also being able to prove that, say, Alice closed out the loan, she returned the USDC to Bob, and then should be allowed to withdraw her original collateral. So all types of systems like that you can build around this core HBitVM proof system and adding in another application-specific proof, whether that's a proof of what a certain oracle says about a certain exchange rate, or a proof about, Alice's and Bob's transaction flow between them, whether Alice has repaid the loan or not, things like that. You can add those on sort of as Lego blocks on top of this unified single proof system that gives you the baseline of knowledge of each of these chain states to build all these different types of applications very easily on top of it.
That's actually super important, because we're not the arbiters of everything that you can prove with this. We're providing pieces, we're providing a system, and we're providing an initial use for it. But anyone out there who's a builder who wants to do something with these pieces can and should. That's the whole point, where one group provides one piece, another group builds another piece, and other people out there can put this all together in new and interesting ways that we haven't thought of, because honestly, we're spending a lot of time building it that we're never going to think of every possible use case for it. So anyone here who's watching this, think of use cases for it. Go build something, do something with it. Take the pieces we provide and do something we hadn't thought of with it. Hopefully something good, but
And just to give a few ideas on that, beyond using it for, settlement or verification of some, external state on Bitcoin to conditionally control who's able to access, the underlying Bitcoin that's held in one of these ZK secured vaults. You can also do stuff that is entirely outside of the Bitcoin ecosystem while still inheriting that Bitcoin security for Ethereum ZK proofs. So one of the things with ZK proving in general is the whole, by definition, a ZK proof is zero knowledge, which means even if you don't care about that property, whatever information was used to construct the proof, generally speaking, is not available. There's ways that you can reveal some of that data, and that's basically how you output something, quote unquote, output something out of a zk-VM guest program. But the fundamentally, when you look at the Ethereum ecosystem, ZK proofs of Ethereum that are used in systems today do not carry enough information to inherit the full economic security guarantees that people expect from Ethereum. So Ethereum uses a variant of proof of stake that is slashable, which means if somebody misbehaves in the system, somebody else can observe that misbehavior and then prove that misbehavior back to the protocol to slash the participant who misbehaved. As an example, say somebody controls, 2/3 of the Ethereum staking power somehow. Maybe they compromise multiple different, large staking providers or whatever, that they get access to a bunch of staking power and they want to attack the network and perform a reorg, which means they create this alternate version of the chain history and try to convince the network that their alternate version is the correct version, not the current chain that the rest of the network is looking at. And in order for them to do that, in order for them to reorganize past a safe or finalized block on the Ethereum network, they would need to sign competing blocks that they already attested to or already sort of agreed were correct on the canonical chain. And so then there's a cryptographic proof that they misbehaved because they initially voted for the current canonical chain. That's what allowed it to finalize. But then they voted for this alternate chain that conflicts with what should be the canonical chain that they previously agreed to. And so if they were to do that on the normal Ethereum network and they were to propagate their alternate attacking chain over peer-to-peer, anyone could observe the chain that they previously knew about and then this new attacker's chain, and they could extract enough information to cryptographically prove that a certain set of participants in the Ethereum proof of stake system misbehaved by double signing, or either double signing blocks for the creation of the block or double signing attestations to blocks in the competing epochs, and they could submit that to the Ethereum protocol, and the Ethereum protocol would then slash those misbehaving users. And so in reality on Ethereum, that means if somebody 51% attacked Ethereum and was able to create a alternate chain with enough consensus power that it looked equally valid or more valid than the current chain on Ethereum, then a very large portion of the Ethereum active validators must have misbehaved, and that could be proven to the protocol, and they could be slashed. And you're talking about, multiple tens of billions of dollars of economic value today being slashed for that misbehavior. But with ZK proofs, you don't have that same security guarantee because the attacker who generates that alternate Ethereum chain, they can keep it private, but they can construct a ZK proof of that chain. And then whatever application is validating that ZK proof cannot tell the difference between the correct canonical chain that the whole world knows about or a alternate perfectly valid looking chain that only the attacker who created that ZK proof knew about. And so you can introduce other systems like having some sort of a watchtower system where different people attest to their public knowledge of that chain or something, but then you're introducing additional ways that the system can fail and additional centralization pressure on the system. And so with HBitVM, part of the innovation is that we are forcing the attacker who's generating the alternate Ethereum chain, if someone's actually trying to attack the system, if they generate an alternate Ethereum chain, they have to publish enough information about that alternate Ethereum chain they're building to Bitcoin publicly that would allow somebody to observe that misbehavior and submit a cryptographic proof of that misbehavior to the Ethereum protocol to get them slashed. So basically means that you can now use ZK proofs with the same economic security guarantees of normal Ethereum consensus for the regular Ethereum peer-to-peer network. And so even if you don't have any interest in building a Bitcoin specific application, and say you're just building a bridge from Ethereum to another blockchain and you need to validate Ethereum state, you could use a portion of the HBitVM proof system to get very secure proofs of Ethereum state that, again, cannot be manipulated with the same economic security guarantees of normal in the clear Ethereum proof of stake consensus, and then use those in your system, and you're benefiting from Bitcoin's proof of work acting as a security anchor that ensures that crypto economic security, even though you're not doing anything in the Bitcoin ecosystem with it. So also you could use it for creating very secure proofs of Bitcoin state. So since Bitcoin, again, lacks self-introspection, and also Ethereum can act as sort of this external observer of Bitcoin consensus through the way that Hemi is aware of Bitcoin consensus and ultimately makes Ethereum sort of aware of it by proxy of the DA publications of Ethereum data containing those Bitcoin attributes deposited transactions that carry that Bitcoin consensus information. You can make a Bitcoin like client system that uses ZK proofs of Bitcoin, but they're secured by Ethereum proof of stake to ensure that this is actually the canonical Bitcoin state that the world sees. And so there you're not using Ethereum proof of stake as a way to, ensure somebody who created an alternate Bitcoin chain would be slashed or something like that. But instead you're using Ethereum proof of stake as an anti-censorship mechanism to establish a global view of the canonical Bitcoin chain that anyone can contribute information to, and thus nobody can censor, to do a Eclipse attack or something like that on light clients in that system. So again, not a direct DeFi use case of it, but a way that you can basically use Ethereum proof of stake to make ZK proofs of Bitcoin for Bitcoin only applications more secure, or use Bitcoin proof of work to make ZK proofs of Ethereum state more secure, even if they're not being used in a context that sits between both chains, like the way Hemi's using it for the HBit VM tunnel system, being able to, again, tunnel Bitcoin natively into Hemi BTC and then out into the broader Ethereum ecosystem.
And anti-censorship properties are more important than you might naively realize, because deep down, any of those consensus attacks are expensive. Censorship style attacks are almost always going to be cheaper by, I mean, if I make up a number, it'll be wrong, but it's dramatically cheaper to mount any sort of censorship style attack than any consensus attack. So getting some extra anti-censorship properties, I guess, into whatever you're doing is valuable.
And also, sorry, Rick, with the
Sorry about that. I jumped the gun.
I was a little late on unmuting. One other minor comment on anti-censorship, and it's not really related to ZK, but it's still interesting. So usually L2s inherit anti-censorship abilities to some extent from the base L1 that they are an L2 of. And so, for example, an Ethereum L2 can get anti-censorship from the Ethereum chain, where you can have this sort of alternate transaction submission route where somebody submits a transaction that they want to run on the L2, but they submit it to the L1, and then it's forcibly included in the L2. And so that if you're curious about the mechanism that allows Hemi to use Ethereum as an anti-censorship mechanism for Bitcoin consensus, it's through that same mechanism where anyone with this future upgrade to the Hemi protocol we're working on to enable this whole HBit VM proof system, anyone can submit Bitcoin block headers basically to the Ethereum base layer that get converted into these Bitcoin attributes deposited transactions and pulled up into Hemi. And then likewise, you can also, since we're also an L2 to Bitcoin, you'll be able to use Bitcoin as the anti-censorship layer in case Ethereum itself is getting censored for other use cases. So you couldn't use Bitcoin as anti-censorship of Bitcoin knowledge, because that's sort of recursive and collapses in on itself. But if there was say censorship on the Ethereum side for a transaction, just a regular HVM level transaction on the Hemi network, and for some reason there was censorship on the Ethereum side for some period of time, you could also relay that transaction through Bitcoin, and Hemi's knowledge of Bitcoin through that embedded Bitcoin indexer could similarly pull that transaction data from Bitcoin and execute it on the Hemi L2, bypassing the Ethereum censorship component.
And one other thing that, when we say censorship, normally the word censorship implies a government doing something. That's not strictly what we mean here, because censorship can be a bunch of miners don't want to include something. A bunch of validators don't want to include something. It could be you're a light client and certain participants on the network want to keep you from seeing, and this is going to sound real conspiracy like, they don't want you to see the real state of things. This isn't They Live, so that's not exactly what I mean, but censorship doesn't strictly mean the government version of it. We just mean other players on the networks that we're talking about that are preventing you from either seeing or sending information that you want.
All right. We are moving on to our next question. Coming in, Yahoo's asks, one of our community moderators. Hey, welcome. In ZKs, we're doing this live. Let me take that one from the top. In Hemi's ZK provability design, how is data availability guaranteed for the state transitions being proven, especially if proofs are generated off chain?
That's a good question. So, and there's actually a really important component of ZK proving chains in general is data availability. So a little bit of context, Hemi itself uses Ethereum as a DA layer. And in the distant future, that may be converted to a Hemi-powered external DA system powered by like VE Hemi economic security or something similar, like we're building out for Chain Builder. But fundamentally, in its current state, the data for reconstructing the entire Hemi chain is published to Ethereum. And then the ZK proofs that are used to settle anywhere not only prove the Hemi state transition, but they prove the correct extraction of the data that constitutes the Hemi chain that results in those state transitions on Ethereum itself. So with the HBitVM proof system, we have this way, again, using Bitcoin and Ethereum together to establish this known canonical state of both chains in a very secure manner. And so in addition to proving, Hemi is transitioning from block 100 to 101, it has these transactions in it. When you execute it, you move from this state root to this state root, and then its embedded indexer moves from this state root to this state root because you process this Bitcoin attributes deposited transaction. We're also proving that the actual data which constitutes that Hemi block is published in a DA blob to the current known canonical Ethereum chain. And so it sounds a bit like a snake eating its tail. And so there's a couple tricks you have to use in order to basically build the chain sort of by pieces. So in your ZK proving system, you prove that Ethereum has advanced sufficiently far enough that you can finalize a certain chunk of Ethereum state based only on Ethereum consensus. And then you prove DA extraction from that. So you say, okay, let's prove that in this segment of Ethereum blocks, that the only DA blobs that are valid that pertain to the Hemi chain are these DA blobs. Here's a KZG proof, that KZG inclusion proof that proves that those blobs were actually committed to in the Ethereum chain. And then here's the actual data that represents those blobs. Here's a ZK proof of running the extraction algorithm that takes those blobs as part of the block derivation pipeline, converts them to valid L2 blocks. So here's, we have this blob of data. We prove that it's in Ethereum. We prove that when you run this extraction algorithm on it, you get these resulting Hemi L2 blocks. You prove that those Hemi L2 blocks connect to existing known canonical Hemi state based on, and this gets kind of recursive, but on a previous ZK proof that did the same thing, and then this goes all the way back to Genesis. So you have a known Ethereum state from a previous ZK proof that also has a known Hemi state and known Bitcoin state. And then you build another segment of proof on top of that, that again proves that we continued the Ethereum chain with these additional blocks. We extracted this Hemi L2 relevant DA blob data from that Ethereum chain. We processed it through the block derivation pipeline to get these actual Hemi blocks. They connect to the current Hemi chain that we're building on top of. And then that's where you then build the where you add the state transition proof of the Hemi L2 blocks themselves. So you have all the scaffolding before you actually get to proving the state transition of a Hemi block. You're proving all the scaffolding under it to prove that that is actually a valid block of the Hemi chain that you should be computing a state transition for in the first place. Hopefully that made sense. There's a lot of layers to it. In the HBitVM white paper in section, let me find it, almost there. Section 5.5, we have the full algorithm that sort of separates out those layers and lets you kind of visualize, and we should add a picture for this, but sort of the layered stacking of these different ZK proofs of different parts of the protocol that build, each layer builds the foundation that the next layer needs to be able to do its job, knowing that the data it's actually using for its job, say proving state transition, is correct and is actual data that should be in the first place allowed into that layer of the ZK proving system.
All right, we are moving on to a comment that came in on Twitter. I refuse to call it X. I apologize. All right, the Hemi Bros DAO asks, is Hemi's proof-of-proof technology patented, or can other blockchains replicate the technology?
So it is patented. We don't currently have licensing for other projects to use it, although definitely open to ways to do that make sense and are interesting. In general, though, for all of this ZK proof discussion, you wouldn't need to hold a patent for, or you wouldn't need to hold a license for the patents that cover proof of proof in order to use the ZK proofs that Hemi Network generates as a public good to do stuff that benefits from the Bitcoin security you get for these ZK proofs, if that makes sense. So the actual algorithm for the way of incentivizing the decentralized publication of one chain state to Bitcoin or generically to another blockchain, and then using that as the basis for fork resolution and consensus protocol, those are covered by patents. But if you're using a ZK proof that benefits from the HBitVM proof system, it basically uses the proofs themselves and then extends on them with an application-specific proof, that would not be using the POP patent in any way. You're not implementing the algorithms in any way. You are reusing an existing proof that's generated by a system that itself is using proof of proof to create these secure proofs, and itself is licensed to use the IP. So short answer, yes, but for all these ZK discussions, other projects could extend the ZK proof system completely permissionlessly because they wouldn't be implementing anything that's covered by proof of proof patents.
All right, let's move on. Let's see. Nabil619 asks, how about building a ZK proof cross-chain identity for giving wallet reputation score?
ZK proof cross-chain identity. Yeah, it's definitely a interesting use case of ZK tech. So not something that we're necessarily focused on. I will say as an aside, one of the things that I think is underserved in the space is identity, and specifically identity in the context of like a self-sovereign identity that you own, you control, and is based on your own interactions with or across the blockchain ecosystem. And so there's a lot of ways that ZK does intersect or could intersect with identity protocols. So sort of one of the classic examples that people give of ZK proving as sort of an easy real world example is, say you want to prove that you're over 18 because you want to rent a car or whatever, but you don't want to show somebody your full ID. You could have a ZK proof of your ID that proves the computation that age is greater than or equal to 18 without revealing your name and your address and your biometric data, whatever else is on your ID. And so taking that same analogy into the blockchain world, into ZK, you can do a similar thing where you have this self-sovereign identity that you either A, build over time by putting your own information into it, like, hey, I'm, this is my username on this social media platform, and this is my public key for signing this type of message and whatever. and also from everything that you authenticate under the same single identity, all of your actions across the blockchain ecosystem. So you could conceivably build a ZK proving system built around that sort of identity protocol, where you could prove, here's a ZK proof this user has a certain trading volume on this DEX on base. And here's a proof that they have this amount of Hemi BTC staked in the Hemi earn product on the Hemi network. And here's a proof that they have, this outstanding native Bitcoin DeFi loan that's run by a like HBitVM powered Bitcoin backed loan protocol. And here's proof that they did this thing on Ethereum. And so you could add all these ZK proofs together and create this like single ZK proof that proves the sort of global state root of all of these claims about user activity across the ecosystem. So I do think that's an interesting use case. The complexity of it is it requires every data source you're pulling from to be ZK proven, or for you to implement the ZK proving for that system. And so I think building something like that today is very difficult. You'd have to basically stick to just ZK proven chains, or you'd have to build all these custom ZK proving systems for all of the chains you want to include. But with the HBitVM proof system, at a minimum, you would be able to do it for Bitcoin, Ethereum, Hemi, and then with relatively easy extension, any L2s that use Ethereum for DA. And so that could give you kind of a baseline to build that sort of an identity system, at least in that fairly large segment of the blockchain ecosystem. But then if you wanted to prove that, hey, the user did this thing on Solana, that's an entirely new proof system that you got to implement to prove things about Solana activity, for example, and then associate those with that user identity. So it's not something that we're currently building. I do think it's underserved in the space and there'd be a lot of utility for it. The complexity is, again, that all the data sources you're using do have to have a ZK proving system for them that is not only built, but also maintained when they fork, when there's protocol changes, stuff like that. But HBitVM proof system, what we're building, does sort of lend itself to building that sort of a system, at least in the Bitcoin and Ethereum ecosystem world. And then you could extend that to, again, pulling stuff from other L1 ecosystems.
Identity is very hard, is one of the things it comes down to. And,
Yep.
like we had this years ago with PGP and, signing things, and you end up with this web of trust. And one of the deep sort of not really solved problems, which again, PGP and web of trust type of things try to solve, is how do you connect? How do you have a one-to-one connection between an online identity? So if I prove that wallet A has done something on a bunch of chains, I still don't prove that. It still doesn't tell me much about who controls wallet A. So that's not really a fully solved problem. And ZK stuff, especially the things in Hemi, give you one more tool to help work to solve that problem, but it doesn't solve the problem for you. And even before you get to all the problems Max brought up, like what about chains that don't support it? Or Solana's a problem all by itself always. I'm sorry, you brought it up. There's no way I was going to let that just slide without anything. Thank you. Thank you, Rick. But there are other unsolved problems in identity, not the least of which is how do you connect identity from online to offline? How do you show one-to-one relationships with identity? So even if I prove that this is connected to this, it doesn't necessarily show that the one-to-one connection goes both ways. And if you have ideas in that space, that is awesome. I would love to see. We need more new ideas in that space because it's unsolved. So people should be throwing ideas out there, should be implementing proof of concepts in it, should be trying things. And you know what? Eventually we'll see which one of them works. Let's, have our tenses lined up there. But so I would love to see people do something there. And I hope
also, go ahead.
Nope, that was the end of it.
I was just going to add to that, like John was saying, the proving the link between the real world and on-chain world is really difficult. So, usually, obviously, the design pattern is use an oracle. So you have this trust layer where you have a company or a government or whatever that would attest and say, yes, that person who is Max Sanchez with this social security number and whatever is the person who controls the private keys behind this address, right? And then your identity sort of flows out from there for anything that needs to be cross-referenced against the real world. But there is there's at least one project I know of that's doing some interesting stuff. And this isn't really related to Hemi, but it's interesting, and there may be sort of an intersection in the future where they're using ZK proofs of biometrics, and they're specifically biometrics that the average phone can collect. And so being able to say, prove you have basically a program that analyzes your camera's data feed and looks at your face as you move it from side to side, kind of like the traditional KYC people are familiar with doing on sites that require you to move your face to the left and move it to the right and get closer to the camera and all those things. But it does that completely locally with a ZK proven guest program that is doing all these verifications and extracting all this biometric data, and then constructing a ZK proof that the person actively using the device has the same biometrics as the person who originally set up, say, this Ethereum account or whatever. And so it's not a full, proving that you are this specific individual based on a government registry sort of a thing. But it does serve a lot of the use cases of, things like social recovery, things like being able to, it's a multi-factor authentication that you could use to not just have to sign, say, large transactions over a certain dollar size with your private keys, but also to need to prove that it is someone with the biometrics you originally committed to on chain that is using the device that is submitting that transaction. And there's probably a lot of other interesting ways that could play into identity protocols as well. So it's ZK relevant, so I thought I'd mention it today because that's the topic of discussion. Again, not directly related to Bitcoin or Ethereum or what Hemi's doing, but since we're talking about identity, there's some interesting solutions in the space that sort of solve or try to solve that real world bridge. Obviously, the problem with that is the verifier for that biometric data would have to be more than likely open source. And so then anyone who wanted to manipulate the system and construct invalid proofs could try to find ways to feed invalid or faked or mocked camera data, quote unquote camera data, to that ZK guest program and try to get it to reveal a false positive. So again, I'm not the one building it, so I can't speak to the details, but there is some interesting stuff on the connecting real world to on-chain identity using ZK proofs of biometrics that are privacy preserving, but give you that at least theoretically extra layer of security and proving that you are who you say you are, at least for some definition of who you are, as in, again, on-chain biometric commitments or something.
Based on one of the examples you said about using ZK proof as opposed to like a physical ID, imagine doing that at the airport, how bad you would piss people off.
I don't think TSA would accept that.
I don't think they would either.
I swear I'm Rick, but I'm not going to prove it. I'm just going to prove I'm going to prove I'm a U.S. citizen. I'm not on a do not fly list. Here's a cryptographic proof. Here's a verifier program. Let me explain how it works to you.
Or when you try that at the grocery store to buy some beer or something, it's like,
Yes,
everyone get comfortable. It's going to be a while.
Yeah, go to the other lanes, guys. So, no, not to make a bad pun, but yeah, I don't think that's going to fly at TSA.
Oh. Thank you for the setup. All right. Moving on to our next question. What is the difference between HBitVM and BitVM?
Good question. So BitVM was there's a couple different layers to this. So BitVM was originally a design back in, I think, like October of 2023. It was a very simple proposal, but very powerful for how to theoretically prove or verify any computation on Bitcoin, with the key unlock being that Bitcoin script is expressive enough to build logic gates that themselves could be used theoretically to build any finite program. And that then you could use this bisection algorithm between two parties to bisect through a computation if there's a disagreement on the computational results. So you have two parties who agree to a computation in the first place, a computation that verifies a game of chess or something. And then you have if both users don't agree on the computation, so Bob thinks the computation resulted in this value, which means he should get the Bitcoin, and Alice thinks it resulted in this value and that she should get the Bitcoin, then they can engage in an on-chain fault dispute system to bisect through that computation and in some way get to the part of the program that they disagree on. And so actually the original design I don't think covered the bisection game. It was just about creating the circuit itself, and then later the bisection game was introduced. But so that was the original BitVM design, was sort of this two-party design, but it was an arbitrary computation on Bitcoin, which was previously not possible with what anyone else was really doing on Bitcoin, at least natively, where you could gate the execution flow of a Bitcoin transaction, such as releasing Bitcoin to a certain spender, based on the satisfaction of an arbitrary program that is pre-agreed upon ahead of time. Then BitVM2 was a major expansion of the sort of core concept of BitVM, but that then introduced, basically made it practical to use for a bridging, or in our case, a tunneling protocol. And so BitVM2 not only had the ability to verify some arbitrary computation on Bitcoin, but also to do it between any arbitrary permissionless parties. And so it's no longer this two-party setup where you had Alice and Bob, who are known at the construction time of the protocol and agree on the computation ahead of time and then challenge each other. You can have this permissionless challenge system where you could have this setup of a computation that a certain participant in the system needs to provide input data for, that ends up, when fed through the computation, results in this result. And so the practical example of that is you have a ZK verifier, and you have to, the operator in the case of a bridge design, for example, has to submit a ZK proof that when run through that, Groth16 verifier implemented as a Bitcoin program with BitVM, results in a certain value that allows the operator to unlock the UTXO. A little more complex than that because you have this Bitcoin transaction probability graph that's pre-created by using something called covenant emulation. So it's basically a way to enforce different potential execution paths across multiple Bitcoin transactions and enforce sharing of data where relevant between multiple Bitcoin transactions. So it's not as simple as ZK proof unlocks a Bitcoin UTXO, but that's sort of the end result you get to with a BitVM2 style construction. So that was BitVM2. It was basically making BitVM the philosophical approach behind the original BitVM into an actually practical system that could be used to validate a relatively large complex program like a Groth16 verifier in Bitcoin very efficiently without having to go through this bisection game. And so you no longer had to have one party defend and one party attack, and basically have log base 2 of the total compute complexity of the program as the number of steps required on chain, which makes proofs very, very expensive or it makes disputes over proof verification very, very, very expensive and very long to do on Bitcoin. We're talking, it could be, depending on the timeout parameters and stuff, 1 month, 3 months, 6 months to go through a full fault dispute game over a fairly large program. And so,
and it's really important that if disputes are long, that means the amount of time funds have to be locked up before they can actually do anything with them is long.
Yep.
And even worse, if proofs are expensive, the likelihood of someone wanting to claim a probably bad transaction as bad goes down. So ironically, by it being more expensive to do that, you make it less likely that you take advantage of the security that you have there.
Yep. And it also creates a griefing vector. So somebody can say, hey, and again, you can design the system with the right economic balance to resolve this issue, but at least in most cases, but it complexifies your economic design because you now have a system where somebody can pay an amount of money and basically delay the correct final execution of the system for a long period of time. So you could go in a system that didn't have economic incentives set up correctly. Somebody could come in and say, hey, I'm going to dispute your proof unless you pay me a ransom of 0.5 Bitcoin. And maybe the operator is withdrawing 100 Bitcoin and their cost to capital is much more than, you know, a 0.5% of the total value that's going to get locked up for a 6-month period. And so there's the length is not only, you know, a really bad experience for the people on the system, but it's also a potential griefing or sort of ransom attack vector, depending on where exactly the, you know, potentially long compute is and how expensive it is for somebody to trigger that maliciously to force that bisection game to occur. So BitVM2 got the important point is that BitVM2 got rid of that bisection game, which was part of sort of a, you know, BitVM 1.1 design, if you will, and replaced it with what's still a very expensive on Bitcoin verification. But basically what they did is instead of this bisection game over, you know, execution of a CPU that's emulated in Bitcoin script, a little bit of a hand wave explanation without really getting into the details, but they replaced that with implementing a program in Bitcoin script that you break up into chunks that each are small enough to be brought on chain and executed with the regular Bitcoin script execution environment or execution engine. And so the way that they did that was they said, okay, we have this giant, say, 2 gigabyte program in Bitcoin script that actually does implement a Groth16 verifier. But you can't run 2 gigabytes of Bitcoin script in a single Bitcoin block. That's a Bitcoin block's 4 megabytes. And so there's no way to run this computation directly on chain. So we're going to break it out into a bunch of separate tiny little chunks that are each a little smaller than 4 megabytes so we can bring them on chain. And what we're going to do is have the operator who is claiming that they have a valid ZK proof that when processed through this giant 2 gigabyte program produces the output that allows them to unlock the UTXO. We're going to make the operator commit to the intermediate states of data between each of those chunks. So to give a simpler example, if you had a program that said, you know, we're going to run SHA-256 100 times, and you broke that up into 100 different single invocations of SHA-256 that each calculated SHA-256 on the output of the previous SHA-256 run, then the operator would be committing to each of the mid states, which would be each of the, you know, you have your input, which you commit to, which is, say, you know, private data. And then you have the intermediate state. The first intermediate state would be the first SHA-256 hash of that input data. And then the second intermediate state would be the second SHA-256 hash. And so and obviously it's much more complex for something like a Groth16 verifier. You have, you know, mid state that's different mathematical values of different things that are going to be used in the next part of the computation for validating this, you know, pairing relationship between numbers. And so the point is, though, you can break a program up, you can grab these mid states, and you can break the program up intelligently to try to minimize the amount of data that has to be transferred between parts of the program. So you can kind of think of this conceptually as, you know, say you had a program that did some really complex thing, but it did it in 2 chunks, and there was only a small amount of data that was passed from like phase 1 to phase 2. If you broke it up between phase 1 and phase 2, you have very little data that's getting transferred between the chunks. But if you broke up phase 1 into 2 chunks, for example, you'd have potentially tons of data that is still, you know, in registers and in memory, so to speak, that's being actively used by the computation. So you have to chunk it in a smart manner that sort of reduces that the amount of intermediate state between those different program execution chunks. But you have the operator commit to those using something called a Lamport signature, which is a one-time hash-based signature scheme that basically, if you were to sign 2 different messages with the same private key, anyone could cryptographically prove that you signed 2 conflicting messages because you'd be revealing enough of your private key for somebody to prove that you signed 2 messages where at least one bit of those 2 messages was different. And so you can use that to force an operator to attest to either obviously the actual ZK proof itself, which is the input to the program, but also all of those intermediate states in a way that then later you can have another Bitcoin transaction in the challenge path that forcibly brings on whatever either input to the first chunk, or one of the mid states that a challenger believes is the part of the Bitcoin transaction or is the part of this giant broken Bitcoin script where the execution diverges. They can bring that single chunk on chain. They can replay that operator's commitment, and there's no way that the operator could lie about having committed to different data, because doing so would be double signing with a Lamport signature over different data, which would reveal enough information to prove on chain in Bitcoin script that they signed two conflicting messages and thus are also misbehaving. So that's sort of the BitVM2 design. I realized I got a little off track there.
One bit I just to make that a little more understandable. The use of the Lampert signature is actually as complex as it sounds. It's really just a very clever hack to get around the fact that in Bitcoin, you don't have state that you can save for transactions across blocks. It's not, you have more state accessible to you in Ethereum than you do in Bitcoin. And so people needed, the BitVM people in particular, needed to come up with clever ways to sort of fake, saving data in a variable and having it accessible for transactions across blocks. And the Lampert signature, for as complicated as that sounds, it's actually less complicated, and it's just a very clever hack to get around that.
And the basic theme of anything BitVM related or ZK related when it comes to Bitcoin is it's usually really easy to do this thing in Ethereum, but on Bitcoin, since we don't have a Turing complete language, Ethereum's not technically Turing complete, but a Turing complete language in air quotes, and the ability to have shared state between transactions and a common data storage model, and because we don't have self-introspection on Bitcoin of the current context of the Bitcoin chain that the transaction's executing within or the Bitcoin script's executing within, all of these limitations of Bitcoin end up creating these really, really complicated systems that have to work around these limitations in some way. And so that's a theme you'll see again and again with various parts of just BitVM designs in general and HBitVM, especially with getting around HBitVM's primary innovation is, again, getting around that lack of Bitcoin context that when combined with the other solutions in the space based on BitVM2, BitVM3S style designs lets you, verify a Groth16 ZK proof on Bitcoin and do that relatively computationally efficiently with BitVM3S, things of that nature. But the overall theme you'll hear again and again, this applies to the use of Lamport signatures, is these are, clever workarounds for limitations of the Bitcoin protocol that let you do things that, generally speaking on a chain like Ethereum would be easy, but given Bitcoin's architecture, you have to come up with these weird workarounds that make sense, but they're definitely not intuitive and definitely not the most efficient way if you were building a system from the ground up that, if you're rebuilding the Bitcoin protocol and adding features in to enable stuff like bridges and ZK verification for, vaulted Bitcoin for different applications and stuff, you design the Bitcoin protocol a lot differently. But with the Bitcoin protocol as it is, you have to design all these complex workarounds to, synthesize this sort of behavior in these roundabout ways. And I did get off topic a little bit. The original question was HBitVM versus BitVM2 or BitVM. And so that was a background on what BitVM and BitVM2 is. To finish that out, BitVM3S is basically an extension of BitVM2. So it's the same trust model where you can have anyone do a permissionless challenge of an operator's claim to bring a portion of the ZK proof on chain. But it uses an approach called garbled circuits to basically trade off needing to do a large chunk of computation on Bitcoin for needing the participants in the protocol to store these very large garbled circuits that represent the actual ZK verifier program. And then the on-chain part converts to just a very small opening of a portion of the garbled circuit that actually proves incorrect execution based on the operator's sort of opening of that garbled circuit by providing decryptions for the input wires that correspond to their ZK proof. So it doesn't make the system, quote unquote, more efficient overall, but it shifts the cost from these really expensive on Bitcoin verifications of basically taking up an entire Bitcoin block, so to speak. Again, you could chop it up a little smaller and take up half a Bitcoin block, but the point is taking up a ton of space on Bitcoin, paying tons of transaction fees to do that, to bring that disagreed chunk on chain to resolve the dispute process. And it shifts that to off-chain, where now you have to store this giant garbled circuit, which is 200, 300 gigabytes. It obviously depends on the complexity of the program you have, but the on-chain verification of misbehavior is a lot cheaper because it's just proving this very small, incorrect opening or incorrect execution of the garbled circuit. So that's the BitVM landscape. And then there's other offshoots like BitVMX and some other designs that have different trade-offs and work a little differently. BitVMX, for example, implements or simulates a full CPU, kind of like the original BitVM 1.1 design. The name was a little overloaded with different things under the BitVM name itself, but BitVMX kind of goes back to that original design, but has a lot of optimizations to make it practical on chain. They do have a bisection system, but it's configurable, so it's not just log 2 of the complexity of the program. You can configure that to bisect in larger chunks and things of that nature. So that's sort of the BitVM landscape. And then what HBitVM is doing is building on top of the BitVM 2 or BitVM 3S style designs, where you have permissionless challenging. You have the ability to construct this transaction graph using covenant emulation, where the system is secure unless all of the participants in the system collude. So kind of like at least metaphorically similar to a like the KZG setup ceremony on Ethereum, or the trusted setup ceremony powers a tau for like a ZK proving system or whatever, where as long as one participant is honest and deletes their toxic waste, the entire system is secure. You have a similar thing with BitVM 2S, BitVM 2, BitVM 3S style designs with covenant emulation, where as long you can have a group of 100 or 1,000 participants who all collectively sign this Bitcoin transaction graph, and as long as one participant deletes their keys, nobody can construct a alternate Bitcoin transaction graph, which is the kind of final piece to enforcing a predictable execution path through a DAG of Bitcoin transactions in a way that you can enforce sort of this flow control across multiple transactions on Bitcoin based on certain conditions in the previous transaction. So where HBitVM differs is we're building on that entire core basis, but what we're doing is we're making the ZK proof system more secure. So the ZK proof that you're validating in a BitVM 2 style design, with HBitVM, we're making that proof secure and self-contained in a way that's not being done with other BitVM 2 based designs. So the original BitVM 2 canonical design used something called superblock light client emulation. So this is where, again, Bitcoin lacks self-introspection, and since Bitcoin can't see itself, you have to have some way externally to come to a decision on what is considered a canonical Bitcoin block and somehow feed that into your ZK verifier, so that the ZK verifier could say, assuming, given this Bitcoin block is canonical, then the operator in the system behaved correctly. And so for HBitVM, we wanted to get rid of that superblock light client emulation system, which we cover this in the white paper if you're interested in the nitty-gritty details and sort of an economic analysis. But it's very easy for a Bitcoin miner to attack the superblock light client emulation system by withholding a Bitcoin block that ends up being or appearing to the protocol as the best superblock in a certain observation period, and then they can do a griefing attack against the operator by telling the operator, even though you committed to the correct superblock that you observed, we have a private superblock that we withheld. We only paid the cost of, giving up a Bitcoin block reward, or in the case of a pool miner, a very small portion of a block reward in order to withhold this proof, or in order to withhold this block. But if we were to release this block to the superblock light client emulation challenge system, it would appear better than the superblock you committed to, so it would make you look like you're misbehaving even though you're not. Therefore, you would lose access to withdraw the 100 Bitcoin of liquidity to make from the ZK vault to make yourself whole for the 100 Bitcoin of liquidity fronted in the system. So why don't you pay me 10 Bitcoin and I won't release this superblock, this better superblock, and make the system falsely eject you for misbehavior. And so other projects have tried different approaches to work around that, needing that sort of a light client emulation system, but a lot of them introduce additional permission roles on the network, some sort of like a watchtower system that is a certain consortium of participants that are agreeing to their observed version of canonical Bitcoin state. There's other approaches that try to extend the Superblock light client emulation system. I'm not sure if anyone's actively building these anymore, but that basically added additional Bitcoin block validation on top to try to make it more expensive. So the same attack exists, but it's harder for a miner to execute. But what we're doing is bypassing the need for that system entirely. So now we're using Ethereum as the anti-censorship layer for coming to consensus about what the true canonical Bitcoin state is, which means that as long as nobody can exert full censorship of the Ethereum chain, then anyone can contribute Bitcoin consensus information to Hemi's view of Bitcoin through Ethereum, which means that then a ZK proof of Hemi and Hemi's knowledge of canonical Bitcoin state can be trusted with the anti-censorship properties of Ethereum. But then the issue is with just that design, if that was it, is that somebody with a lot of Ethereum staking power, even historically, so maybe they have the thing with, I'm going in a lot of directions, but the thing with BitVM style designs is they have to be configured once and then left offline for a long time. So with a smart contract that's, say, on Ethereum, it can be updated and be changing its state and changing its, knowledge of the current remote state of all these chains based on ZK proofs, and do that every 10 minutes or every hour or every day or whatever. BitVM style designs, the way that you have to build them is all of the information the ZK verifier is eventually going to have, other than the ZK proof itself, but all the context of, current knowledge of the Bitcoin chain, current knowledge of Hemi, current knowledge of Ethereum, it also all has to be baked in at the time that the vault's constructed as basically the configuration of the ZK verification script. And so you could have BitVM style vaults that live for 6 months, a year, 2 years, 5 years, because nobody has withdrawn and actually, unwound that vault and submitted a ZK proof of all of the Bitcoin, Ethereum, and Hemi chain state transitions that have happened since the vault was originally constructed. And so if you're using Ethereum as an anti-censorship layer, Ethereum uses proof of stake. The problem with proof of stake is something called weak subjectivity, which means that somebody with really old signing keys for what used to be a large portion of consensus power, even if they've fully unstaked, so they have no stake active in the system anymore, they can construct what appears to be a valid version of the Ethereum chain from those really old keys. So say you went around to all the largest, Ethereum staking pools and said, hey, you have all these private keys that you're no longer using. They no longer correspond to any actual Ethereum that's staked in the system, but they collectively correspond to 2/3 of the Ethereum staked in the system 2 years ago. Can I buy those private keys from you? And then you could use those private keys to create a 2-year-old alternate version of the Ethereum chain. And if you had an HBitVM, or if you had a BitVM vault in general that was constructed, well, HBitVM in this case, because we're using Ethereum as the anti-censorship layer, but if you had a HBitVM vault that was made 2.5 years ago, it hasn't been able to update its knowledge of Bitcoin, Ethereum, and Hemi state since it was constructed. And so that alternate Ethereum state from which you could derive an alternate default derivation mode Hemi state and an alternate view of Bitcoin, that could all be manipulated by that attacker who's able to generate this very long private Ethereum fork off of these old, no longer in use keys. And so, again, normally on Ethereum, that's solved by the fact that nodes are not going to reorg past a chunk of blocks that they have determined are finalized. But for a bootstrapping client in Ethereum peer-to-peer, you could confuse them with that alternate chain state because to them it looks equally valid from a consensus perspective. And same thing with a long offline ZK verifier of Ethereum state, is that it behaves just like a bootstrapping client. It doesn't have recent knowledge of Ethereum chain state, and so it can't reject a proposed new alternate Ethereum fork because it has no existing knowledge of current canonical Ethereum state to compare it to. And so that nothing at stake problem in zero knowledge proofs means that not only can an attacker with 2/3 or whatever majority your proof system is verifying of Ethereum staking power currently generate an alternate looking proof and avoid slashing because of the zero knowledge property of the proof of their alternate state that keeps it private and doesn't reveal enough information for them to be slashed. But also you have this second long-term zero knowledge, nothing at stake attack, which is somebody can go and acquire in some way these really old Ethereum staking keys, produce this alternate chain and manipulate the system and create invalid proofs that would still be validated by the ZK verifier on Bitcoin that's protecting the underlying BTC in the vault. So the way we solve that is, again, with proof of proof and having enough Ethereum attestation data published to Bitcoin within a certain time constraint of the Bitcoin timestamp relative to the Ethereum timestamp to make that chain, that alternate chain, slashable, which means you've solved the zero knowledge, long range, nothing at stake attack. Because if you were to get Ethereum keys from 2 years ago, you can't publish them to Bitcoin state from 2 years ago. You'd have to reorg Bitcoin state by 2 years, which is basically impossible. Or alternately, if you were an attacker who 2 years ago did have 2/3 of Ethereum consensus and you wanted to way in advance plan this attack, you'd have to publish enough information about your currently active Ethereum keys. Well, you'd have to sign your alternate Ethereum chain that you're building in lockstep with the main Ethereum chain, and you have to publish enough information about that to get you slashed while your stake is still active to Bitcoin. So either the attacker reveals enough information to get slashed when their stake is still active, or they have to 51% attack Bitcoin to do a long-range reorg to retroactively insert seemingly valid proofs of their alternate Ethereum state into this fake Bitcoin chain that they have enough proof of work to generate. And so collectively, all of that together allows HBitVM to use Ethereum as an anti-censorship layer for establishing Bitcoin canonical state, which is solving the problem that Superblock light client emulation was trying to solve, but does so in a way that instead of having this, agreement system that tries to come up with a canonical Bitcoin state, uses Ethereum and the full anti-censorship properties of the Ethereum network to establish that canonical Bitcoin state. But then you also have the that Ethereum state that's used to establish that Bitcoin state protected against proof of stake manipulation, again, by using Bitcoin. So it sounds recursive, but the way that you build these in lockstep means they build on each other sort of in steps, in a way, if that makes sense. So that's the difference between HBitVM and BitVM at a high level, is that proof system. We also made some other changes, if you want to dive into the details, then move some of the incentive layer from the underlying Bitcoin transaction graph to the L2, where you can control it more effectively in a Turing complete execution environment. So instead of having to enforce, for example, that a certain amount of collateral needs to be stuck in the system for the entire duration of the vault for each of the operators, you can have the operators, have one single staking position of VE Hemi that's staked on the L2, and that can be used to guard entrance and participation in valid HBitVM vaults. You can also, the protocol can dynamically adjust incentives. So normally with the original BitVM2 style transaction graph, you had to pre-bake in enough Bitcoin into the system, so to speak, to make sure that you could pay fees for the worst case on-chain costs of the entire fault dispute challenge game. And so that made the construction brittle, because if you underpredicted future Bitcoin fees, then the protocol no longer pays participants enough to participate and challenge invalid proofs, but also is very capital inefficient because you have to have all of this capital effectively baked into the system ahead of time. And there's ways that people have found to optimize that to some extent, but by moving those incentives to the L2, where the L2, Hemi is able to observe actual Bitcoin fees and then pay out incentives to the user who successfully permissionlessly challenged a malicious operator based on the on-chain Bitcoin costs that they incurred to do it, plus a profit margin. We make that system more efficient, and then more capital efficient and more secure against Bitcoin fee market spikes. And then the final sort of major piece, which a lot smaller than the HBitVM proof system, but still interesting, is we introduce a MEV marketplace mechanic. So right now, Bitcoin, to interact with Bitcoin, you're basically subject to the existing Bitcoin mempool. And once you submit a transaction, you can do RBF, replace by fee, to bump it in some cases, depending on how much of the transaction you control and things of that nature. But you have limitations in how dynamically you can interact with that Bitcoin mempool. And it's relatively hard to, over time, add additional fees to a transaction or something like that. And so we're adding a Bitcoin MEV marketplace that's coordinated on Hemi buy smart contracts that use HVM to observe Bitcoin state to let people, or in our case, protocols like the HBitVM tunnel protocol, add additional incentives to Bitcoin transactions out of band. And so that gives us additional resiliency that's automatically protocol driven based on observations of Bitcoin fees that we can observe with both pop publications as sort of a sampling of the entire Bitcoin fee marketplace, including dark pool transactions, but that also gives the contract a way to programmatically bump transactions of a certain structure dynamically. And the way that we're designing that MEV system, it's not just constrained to bump this TXID with an additional $10, but it allows more flexible definitions of what transaction construction or template is eligible to collect this bounty. So the protocol can say, for example, any Bitcoin transaction that spends this Bitcoin transaction in the pre-established HBitVM vault transaction graph is eligible to claim this reward. And so then that incentive can apply to any transaction that produces a valid challenge on Bitcoin of an invalid operator's ZK proof, regardless of the actual TXID of that transaction. So it doesn't require a user to say, hey, I submitted this transaction, but I don't have enough Bitcoin to pay the transaction fees, and the protocol subsidizes it. Instead, the protocol can pre-subsidize any transaction that fulfills that part of the HBitVM, execution of a transaction in the HBitVM transaction graph that the protocol needs incentivized without having to choose a specific exact transaction that fulfills that obligation. It can incentivize the behavior, not the transaction itself. So high level, that's not high level, but that's the difference between BitVM and HBitVM. The proof system, Bitcoin MEV marketplace, moving the incentives, or a lot of the incentives and economic disincentives off Bitcoin onto the L2 to make it more efficient. And then more broadly, the HBitVM proof system can be used beyond just bridge or tunnel designs for a bunch of other cool applications. And that, I'm finally done with that. If anyone else wants to add on to that. I think that's no, and we may have killed Rick because I don't see him on. There he is.
I am very much alive. So
just a little sleepy. That's all.
No. I was just checking Slack messages, but for those just tuning in, that question that Max just answered was, Max, what is your favorite type of pie? I'm just kidding. It was a very in-depth response to BitVM versus HBitVM, and we still have quite a few questions on deck. How are we all feeling?
I'm good to keep going. I don't know how everyone else's schedule is. I also realize our question list is growing faster than we're answering them. So at this point, this is an unbounded unbounded AMA.
We could just be here forever. All right.
Oh boy.
Let's text. Oh my, Josh, I'm not asking that. Oh, what the hell?
No, you have to ask it. Yeah.
Now I'm curious.
And now I want to know where your limit is.
All right. Well, the community asks, Max, can you please hurry up with questions?
Yes, we will try to expedite the remainder of this. And also, that was a very deep dive into HBitVM, but now any other questions about it can rely on that sort of basis we've established for the last 2 hours. So hopefully future things can be just segregated to that specific question, not all this background information.
Could you repeat all of that just so we know going forward in case we missed it?
Yeah, sure thing. So
everyone strap in.
And actually, I've not any of the questions so far have really made its way over to Clayton, but Clayton, as far as ZK provability, just for a little bit of context, the part that he's currently working on is integrating ZK proofs of HVM precompiles and HVM state transitions into opgeth. So basically being able to run opgeth in sort of a ZK mode, where instead of it containing a full Bitcoin indexer and validating state transitions and HVM precompiles against that full embedded TBC or tiny Bitcoin state, that it can instead run in this ZK proven context where for each block of the Hemi L2 that it executes, during execution, it can validate that the claimed Bitcoin state transition itself is valid, and that any precompile calls, which is Hemi's way of exposing Bitcoin data into the smart contract layer, any precompile calls against a known Bitcoin state root return the expected result, and then that can be fed back into the EVM for execution. So it's a way to make light clients, sort of full light clients, somewhere in between a full client and a light client that runs, again, with some delay because it needs ZK proofs to be generated, but there's some interesting use cases for it. And then also it serves as sort of an end-to-end testing ability to, as ZK proofs are being generated for this overall HBit VM proof system, for somebody who's generating those ZK proofs to quickly validate that they do correctly prove execution of Hemi blocks with, separating out the layers so they can prove that the precompiles and state transitions for Bitcoin state work correctly in the clear execution of the EVM execution of a Hemi block, and then they can prove the EVM execution of the Hemi block and then validate that somewhere else. So it lets, there's some cool use cases for light clients and things like that, but also is a good testing framework in a way for being able to validate parts of the HBit VM proof system, specifically those precompiled proofs and the state transition proofs, in a live environment that's doing regular EVM execution, and then deferring just the parts of its execution which touch Bitcoin to data that's ZK proven. So I'm not sure if we'll have any questions that really touch on that piece of it, but that's where Clayton is currently plugging into the sort of overall ZK proof system design. I don't know, Clayton, if there's anything else you wanted to add on to that.
No, not much. Yeah, you pretty much covered it. Yeah, it's still in the early development, but yeah, I've been working closely with Max, so I can only take so much credit for the work so far. But yeah, we're getting it written, tested, and yeah, hopefully it'll be ready to use pretty soon. So yeah, we're working on it, and yeah, thanks for explaining it, Max.
I think Clayton's underplaying it a little bit. He listens to me on a call ramble about different architecture designs and things I want to see happen, and then they magically happen in opgeth, and I get to do a code review. So it's
it's fun, man. It's yeah, I enjoy working on it, and yeah, it's yeah, what's the right word for it? It's challenging. Put it that way.
Yeah, and ZK proofs, when you're building, just as kind of a general ZK engineering note, it requires you to think very differently about, computations and how stuff's organized, data's organized, how programs are broken up into different parts. And so as you go through it and, build and design these sorts of systems, you build this intuition for it and, ways of working with it. But for somebody new that's coming into, say, blockchain development, the ZK side of it, at least, maybe they, are existing Solidity developers or whatever, wrapping your head around sort of how these ZK systems work in general, it's one of those things where you kind of just have to go do it and play around with it and reason about it. And then at some point it kind of clicks and the intuition makes sense. And then it's sort of like, learning a new computing language or a new programming language that, works in a fundamentally different, it's say a functional programming language instead of object oriented. Like at some point it kind of clicks and then you understand, okay, here's this different way of structuring problems and, separating out problems into these discrete pieces. And here's what we need to do in this context to actually make it practical to compute this part of this problem with these constraints in this sort of a system. So just as kind of a general note, if anyone's interested in building ZK stuff on Hemi and, building on top of these HBit VM proof system, a lot of this sounds complicated when you first hear it. And to some extent it is, but as you start going through and understanding the pieces, there's actually a lot of analogies between kind of how everything works in ZK and how everything works in traditional computing. And there's sort of a gap you got to bridge. But once that clicks, it's, understanding how all these parts of these systems fit together and why they fit together in certain ways that's useful becomes easier than it sounds. I'll put it that way.
Yeah, just to close out on that one, Max. Yeah, I have to agree. Like when we started the task, it's a lot, right? It's a lot to learn, a lot you feel like you don't understand. But once you kind of start writing the code, and then you start to like run into those like humps, like, oh, where am I getting this data from? How do I verify this? Things do start to come together a little bit. So yeah, I guess I'm just I wanted to close out with that and say to anybody who's hearing us talk, it's not a small number of things out there, but once you kind of get your hands dirty, it clears some stuff up quite a bit. So yeah, I would suggest finding a library or something you would enjoy working on and experimenting with that, and stuff will kind of fall together and you'll hit the roadblocks, you'll hit the breakthroughs, all as you work on it. So that was the last thing I wanted to say.
It's not quite as bad as it sounds. Put it that way.
Yes.
That's a good opportunity to plug the builder role available in our Discord. If you are building on Hemi or interested in building on Hemi, and there's the banner. Excellent timing, Josh.
I'm glad someone's paying attention.
That is how you can get the builder role within the Hemi Discord, which we encourage you all to join. Let's see. When creating smart contracts, is it better to use the immutable or proxy mutable pattern?
So this isn't really a ZK question, so we'll go over this one quickly. Short answer is it depends on what you're doing. So the proxy pattern gives you more flexibility, so you're able to upgrade and change the implementation while keeping your data in the contract there, so you can upgrade a contract without losing the data that's already stored in contract storage. But it also introduces complexity to the system, and it introduces risk of, whoever has the upgrade abilities on the proxy contract can upgrade the implementation beyond the proxy and thus change the behavior of the application. So it depends on what you're building, whether you need the flexibility or not. If you're using an application that uses the proxy pattern for the implementation, where the proxy stores the data and the implementation is the actual logic behind it, it's good due diligence to check on the governance or control of that proxy, who's allowed to upgrade it, whether there's upgrade delays, things of that nature. So it depends what you're building, depends what your requirements are. But yeah, it's a tool, and it can either be good or bad depending on how it's used.
Yep. If you're building something that never needs to be upgraded and that you can guarantee is correct, and where guarantee may mean that you can prove it's correct, then sure, do something without the proxy pattern. If there's potential bugs, if there's a chance that you need to upgrade, use the proxy pattern. It's, that is, unfortunately, there's no one answer to it. The answer is which one's better. If you ask which one's better, the answer is yes.
As with many things.
All right. I am looking over the questions, and Josh, correct me if I'm wrong, but I think we have one more that's strictly geared towards ZK provability, whereas the others, I think we can float over to Midweek with Max, which is every Tuesday at 11 a.m. hosted on our Discord. So please join us there for Midweek with Max. But let me get to this question. In Hemi's ZK provability architecture, how do you handle the data availability problem for cross-chain state transitions, especially when Bitcoin itself doesn't provide native data availability layer?
So I think we already answered either that question or a similar one. So I'll give the really quick TLDR. Basically, so Hemi's using Ethereum for DA. And so there's two parts to data availability. There's the data availability of Bitcoin data itself. So like I talked about earlier, the reason HVM run the full node indexer for HVM runs 2 Bitcoin blocks beyond the current tip is to prevent malicious attacks by Bitcoin miners withholding blocks to cause the data availability issue with HVM. And then there's the data availability of the Hemi network block itself, Hemi network blocks themselves, which for that we use Ethereum DA. In the future, that could be transitioned to a Hemi native DA system powered by VE Hemi staking or something, like we're again building for Chain Builder L3s. But at the moment and for the foreseeable future, it's going to be based on Ethereum DA. And so we're using Ethereum DA to ensure that the Hemi data that we're proving state transitions of and claims about the state from is all available on Ethereum for anyone to be able to reconstruct the state. And then for the Bitcoin side of the DA question, that lag basically ensures that creating a DA fault would be prohibitively expensive, not impossible for even a very large Bitcoin miner to pull off.
All right, let's go. We'll go one more. Just for funsies, what are your thoughts on Python indentations?
Oh God, you should never have a language where white space affects how your program operates. That is just asking for problems.
So in Fortran, you're even allowed to add white space in the middle of words. So like if you have a for loop, you can do F space O space R, and it's the same as using the word for. So yes, white space not mattering has a very long and beautiful, we'll say, history in programming.
Okay, I'm going to change my answer. White space should matter. You shouldn't be able to add white space in between letters of a word and have it mean the same thing. That's too far.
That is totally fair. How about one more little off topic, and then we can go to our wrap up.
Sounds like a plan.
All right. Let's see. What is better, governance staking or boost staking?
I'm not quite sure what this question's asking. So yeah, maybe skip that one. And if we get clarity, we can throw that into midweek.
Fair enough. Okay, we will bounce to the last question. How is decentralized cloud storage better, even though data is split? Is it still secure, given each node only has part of the data?
Good. Actually, this is sort of related to ZK in an indirect way. So I assume they're referring to using a system like Ethereum DA now with the split, where there's basically parts of the DA data are striped across different Ethereum nodes. So no Ethereum node has to necessarily store the full state, but you can reconstruct the state by querying a certain number of nodes across different, it's not subnets in this case, but different Ethereum nodes that store different parts of the DA state. Or other systems like, Celestia, EigenDA, things like that, that let you do this decentralized storage. So is it better than like a centralized provider, like a, Dropbox or, whatever? In general, yes. So you have a lot more redundancy baked into the system. That being said, it's a much different use case than, cloud storage, in the sense of what you use Dropbox to back up your pictures of your kids, right? You're probably not going to go use a DA system for that, although you could. And there's some applications that are trying to build more like generic, consumer-facing cloud storage based on DA type systems. So, at some point that could be something in the future where I obviously encrypt your data before you push it up. The reason the systems stay, and again, secure is kind of a tricky term here, but reliable, perhaps, that you can always recover the data that you push to a DA system, is that there's a bunch of redundancy baked into it. And it's not simple redundancy of like, 5 nodes all store the same first 100 bytes of the data, and then a bunch of other nodes store the second 100 bytes. The way that at least most DA systems work is they use some really clever data checksumming techniques. So without going way into the details, you can kind of think of it like a 2D array of the bits that constitute your file. So say your data is 10,000 bits long, so it's breaks up into 100 by 100 and makes a square. What you can do is you can have parity bits for each of the columns and each of the rows that you add to the system. And so collectively, if you think of a square that's 100 by 100 and you're adding a line of parity bits horizontally and a line of parity bits vertically, that's only an additional 2% of, if I'm doing my math right, 2% of the total size of the storage. But you've now got this interwoven, cross-checked parity bits that it's kind of, in a weird way, kind of like a Sudoku puzzle, where the more of the Sudoku puzzle you have available, eventually there's only one valid solution for the Sudoku puzzle. So it's similar to that in some ways, where if you have enough bits that you're able to reconstruct of the overall data that's being stored, then those parity bits give you enough information to solve the Sudoku puzzle and basically fill in the missing bits. And there's other things that are used to pad in redundancy. JCB, actually, you probably know more about this than I do.
I was going to say one bit that I wanted to say with that is this is not like crazy, newfangled blockchain people stuff. This is absolutely, even in the hardware world, when you think about RAID for disks, having parity disks and being able to, or parity bits being able to reconstruct things by spreading it across things where you only need to have, X number of pieces to save, or, spreading it out across a bunch of disks where you don't need every one of them to recover everything. And that type of redundancy, these are well-known things that like exist in the outside world. It's not just in the decentralized world. And, it's not just blockchain weirdos who want this. This is something that the hardware world, actual, physical things that people have been able to buy for years have done this. So point is, there are well-tested solutions involving parity, involving recovery from, with partial loss of things. So that's all. I just want to make clear that this is actually, despite that, a lot of our stuff sounds like weird magic that only, crazy blockchain people know about and only crazy blockchain people use. There are actually techniques that have been trusted for decades for this. And it just, when you start talking about decentralized storage, you're just using these same techniques that are known, that work, that everyone trusts, that, we're using them in a slightly different location and to a slightly different problem space. But these are already proven techniques. So it's actually a lot safer than you think. It's just when it's, 5 hard drives sitting in a bay on your computer, in your NAS, you implicitly trust it. When it's spreading things across different nodes out there, you feel like, oh, I don't know, is that safe? But it's the same technique. You're doing the same thing. If anything, you're taking away one point of failure, because if, lightning strikes the utility pole by me, it could fry all of the disks in my RAID. It's not going to fry all of the Ethereum nodes out there, unless they're all on US East 1 and Amazon, in which case, we pretend that's not the case.
That's a good point. Yeah, a lot of this stuff has been around since, before I was born. So a lot of this is not brand new stuff. It's, reusing existing, like John was saying, existing parity algorithms we've used for, or modifications, but the same fundamentals as what we've been using for, parity on spinning disks for 30, 40, 50 years. I'll also add to that, there are some, and I'm by no means an expert on this, so I'm not going to deep dive into it, but there are some additional things that have been added in some of the DA systems that do more interesting things that let you, prove that you have a certain part of the data much more efficiently than actually revealing the full data on chain, using different sorts of like pre-built commitments over the data and things like that. So there have been additional things built on top of it that change from, and there's sort of a parallel where, consensus protocols back in the day, consensus protocols have been around for decades and decades before Bitcoin existed, but they were used not for lack of trust, but for fault tolerance. And so you had, old systems where you would use a consensus protocol like Raft to make sure that, 5 servers running in your data center, if one of them is faulty and is producing absolute garbage, that the other 4 can detect that and collectively agree that we don't know what's wrong with number 5, but let's just ignore him for now and continue with the computation. And so with Bitcoin, the one of the breakthroughs was taking consensus protocols and adapting them from that environment of fault tolerance to tolerance against actively malicious parties who are trying to break the system. So if you have 5 servers in a rack, none of those servers are trying to misbehave. One of them just got hit by a cosmic ray and it flipped a bit and they're producing garbage. But the servers aren't actively trying to attack the protocol. Whereas for something like Bitcoin, now you have users who are actively trying to compromise the protocol to get some financial advantage, or their government who wants to shut it down or whatever. And so there's sort of a similar, pun intended, there's a similar parity with these algorithms for, like, say, data sharding, where the original algorithm was meant to protect against unexpected faults where, one of your 5 drives in your bay is going to fail randomly and the other 4 need to be able to reconstruct the data. Whereas now these data sharding systems have to operate in an adversarial environment, kind of like now consensus protocols for blockchain have to operate in an adversarial and not just faulty environment, where they have to protect against parties who could try to, say, for example, maliciously be the one who controls all the nodes that hold a certain part of the data or certain intersecting parts of the data that could cause irrecoverability. And a lot of the ways to solve that are just existing methods we already have for, increasing data parity. But there's also, and again, not an expert, so I'm not going to dive into it, but there's things built on top that provide additional protection or economic guarantees against malicious parties trying to corrupt the system versus the original just, hardware randomly fails environment that parity was originally built for.
All right.
I was going to say one thing. We don't have time to talk about it today, but there's a really cool article that I had just seen that claims that something like 10% of Firefox crashes are due to bit flips and other random hardware memory errors. So that those random error things are actually, it's serious business.
ECC memory exists for a reason.
I'm now terrified that a cosmic ray is going to wipe out my Steam library. so thank you for that new phobia, Max.
You better back up your Steam library to Celestia.
Oh, I can talk about cosmic rays all day, so don't get me started there.
Well, I mean, you are our resident black hole scientist, which hopefully during AI happy hour, that's what your banner says. Let's see. We have one more question. What the hell? Someone's asking me a question. That doesn't make any sense. All right. Well, Rick, are you looking forward to Teach Rick Crypto episode where Max teaches you ZK proofs? Yeah. I mean, yes, I am. That's going to be the Lord of the Rings extended edition of Teach Rick Crypto. So
yeah, clear your calendar for the week, Rick.
Yeah, I hope everyone stocks up on coffee, food, and cigarettes for that one.
We'll be doing practice problems on paper, so bring a pen and a notebook. We're doing problems.
There's going to be visual aids, probably an abacus, all sorts of things.
For some reason, there's what are those drawing tools for like doing geometric proofs? Like a compass, but then there's other stuff too that use for like geometric constructions.
Oh, yeah.
Not a protractor, right?
But that's part of it. But there's like other things that you do. Not just drawing a circle, but like, okay, you need to draw, an ellipse with certain values, and there's ways to do that by hand. It doesn't matter, but anyway, just yeah. We're gonna stuff that shouldn't have anything to do with ZK. It's gonna randomly be there for no good reason.
I don't know. I'm sure we'll find a way.
That might be a few different episodes, but we'll what we'll do is probably for anyone who's interested in watching those, we'll start from kind of like blank sheet of paper, nothing about ZK proofs, and then like what's the motivation for them, kind of what we covered today, but a lot more gradual building instead of like randomly from questions jumping down into various avenues and me getting lost in my own thoughts. So it'll be much more like organized. Why do we even care about zero knowledge proofs in the first place? Where do they come from? Real world physical examples of like what are good analogies for zero knowledge proofs that say use coin flips or cards on a table, or like a guy walking through multiple paths through a mountain, things like that. So more of a like intuitive understanding versus this more like technical sort of deep dive and random walk down different paths of ZK stuff. So it should be a lot more organized and easy to understand.
Well, this was important though, because I mean, ZK provability is something that you've covered numerous times on Midweek with Max, and we've wanted to do the deep dive for a while. So it was important. And I mean, the community showed up, and quite frankly, it was, I think, really well done and very informative. I'm sure a lot of people got a lot out of this too, which is fantastic. I am definitely going to need the more practical examples. And as Josh pointed out, part 1 of 80 it will be for that series.
We're going to run longer than The Office.
Yes.
Oh, man.
We'll be on the air longer than The Simpsons at that point. All right. I think that actually brings us to the end of questions for this. So I got a couple things to plug. One is at the beginning of the show, there was a discount code that showed up. For the record, Max, JCV, I did not write that code. Okay?
I just saw it on the scroller.
I give you my word, that was not me. So I'm guessing you can figure out who it would be. Not to throw him under the bus. But in addition, I'd just like to thank everyone for tuning in today for our deep dive on ZK provability. Please join our Discord community, where every Tuesday at 11 a.m. Eastern Standard, we have Midweek with Max, which is ongoing for we're going on like close to 2 years now. That's crazy. But yeah, every week, live AMA with our co-founder, the engineering team, and usually some special guests from the Hemi team and partners and whatnot. In addition to that, if you are looking to build on Hemi, please join our Discord and apply for the builder role. The builder role gives you access to the protocol engineering team as well as the community moderation team. And that, as John can put it more eloquently than me, John, what do you want people to do with the technology that you guys create?
I want people to build cool shit with the tools we give them.
I could not have said it better myself. With that, I just want to thank everyone, our moderation team, our entire community, all the Hamigos, far and wide. Hope everyone is safe out there. And thank you all so much for attending this session. Our first in what is going to be monthly engineering AMAs that we're going to be hosting live on YouTube, Twitter, and even LinkedIn. I know that infuriates JCV, but that's showbiz, baby.
Thank everyone.
With that, let me turn it over to Max and team for some outros. And I just want to say a very special thank you to everyone again.
Awesome. Yeah. Thanks everyone for coming out and participating in the live stream. If you have any more questions about ZK provability, as it's often a topic on Midweek with Max, feel free to ask questions there too. Or if you're seeing this stream after the live stream and you have additional questions, pop into Discord. We do, like Rick said, a AMA every single week, Tuesdays at, I always get time zones confused, Tuesdays at 10:30 a.m. Eastern. And so feel free to pop in there, ask any questions about ZK or Hemi in general and everything else we're building in the Hemi ecosystem. And like Rick said, we're also going to be doing, starting with this as the first episode, these engineering AMAs roughly every month, depending on events and travel and stuff, because it's more of a production to put together. But roughly every month, one of these engineering AMAs with a specific topic focus. So if you have ideas about what you want the next topic to be, feel free to suggest them as well in Discord or on social media. And we'll be seeing what people are most interested in doing deep dives on and discussing. And yeah, with that, stay tuned for, we're going to be open sourcing a lot of the code for a lot of these components of this HBitVM ZK proof system, and more broadly, the stuff that kind of the scaffolding around it, the smart contracts on the Hemi network that allow it to aggregate this Bitcoin and Ethereum state, and being able to generate ZK proofs of that, the Bitcoin tunnel contracts at a little bit later in the future, but that's coming down the pipeline as well. Oxygen, which is our repo for ZK proving a fully indexed Bitcoin state, both ZK proving state transitions of it and proving what effectively maps to HBM precompile calls. So if you're interested in how to ZK prove Bitcoin for any purpose, whether it's Hemi related or just something you're building in the ecosystem, stay tuned for that to be open sourced as well if you want to either use it or contribute to it. And yeah, with that, looking forward to seeing everyone again on Midweek with Max next Tuesday. And we will see everyone on X, YouTube, and I guess LinkedIn next month as well with another engineering AMA. And maybe next time we'll keep it under 2.5 hours, but well, it depends on the topic.
Let's not book that trip just yet, buddy. But also in the upcoming weeks, please be on the lookout for an announcement about AI Happy Hour, which we'll be hosting. It's going to be a lot looser format, as there will be a happy hour involved. And we'll just be discussing various AI topics. We'll obviously have a question channel open for that. Also, I do need to plug something in the Hemi Discord. One of our moderators, Anubis, is running a gaming session for all the Hemigos for some community engagement. So please feel free to pop in and I believe it's smash cards. Go smash some cards just to decompress. So thank you all so much. We really appreciate it. And we will see you soon.
All right. Cheers.
Thanks a lot, everyone.